Path of the Pole by Charles Hapgood, Part 1. You are listening to Brothers of the Serpent podcast.
Workout guy!
And welcome back, ladies and gentlemen, boys and girls, angels and demons and monsters and serpents. This is Brothers of the Serpent podcast, and we are coming to you not live, as we do once a week, at least, from the 10 by 10 by 10 tangent cube of science, where we are nestled amongst the dusty bones of an ancient seabed, high atop the Edwards Plateau. And I had to get a new podcast app today.
Oh.
The podcast app I've been using for 8 years has finally been discontinued and it no longer works properly.
Oh, man. Was that Beyond Pod?
Yeah.
Oh.
You can't download new episodes. It won't update. I just was like, what's going on? Found out it's discontinued. It doesn't work.
I recommend...
Well, I got Addict.
Oh, okay.
I'm going to try Podcast Addict.
I like Overcast.
Yeah, but that's Apple only.
Oh, they don't... Okay,
Yeah.
never mind.
I agree. Overcast is the way to go if you have an iPhone. But I'm a Droid guy, so going with Podcast Addict. We'll see.
Okay.
Anyway, you know, it is what it is. First world problems, folks.
Yeah, it's a big problem.
Yeah. So the other thing we're doing is we're going to try changing up the format a bit. We're going to just
Had
dive.
a long talk with Workout Guy.
Yeah, that's right. We had a meeting of all the people involved in the podcast, and it took us, after much deliberation, about 30 seconds, we decided, let's try this. Basically, Kyle said, do you think we should try this? And I was like, sure, let's try it. So well, I guess it wasn't everyone involved in the podcast. The watcher wasn't there. Yeah. So it wasn't all hands on deck, but yeah. So we're just going to dive into the main topic immediately, and we'll do all the Space Brother news and everything else at the end of the show.
It's a genius idea that we came up with. No one has ever suggested it before.
That's right. So today we're starting a new book report. We're going to try out The Path of the Pole by Charles Hapgood. I guess, Watcher, do you want to come on and explain some of that stuff you were talking about? You were looking this up. Originally, it was called The Earth's Shifting Crust.
Yeah, so in 1958, Hapgood published The Earth's Shifting Crust, with the big thing being that it denied the existence of continental drift, which the mainstream immediately, said, oh, no, that's not right. But over the next decade, through correspondence with Albert Einstein, he came to a realization that he needed to make some updates to his original theory, and then he published The Path of the Pole in 1970 as his correction to the Earth's shifting crust.
Okay.
So basically, he spent a decade talking with Albert Einstein, and then was like, "Oh man, maybe this guy's onto something."
Yeah, Einstein and others.
Right.
And I think, I think
updates.
I'm not totally sure, but I think isostasy was a big part of this. Like the problem there was, anyway, I've seen some of this. People are saying, well, if there's parts of the crust that are pushed down into the mantle, it's difficult to understand how it's sliding around over top of everything else.
It was partially that, and it had something to do with the ice caps.
Yep.
And his theory on the ice caps, and whether the forces having to do with the shift were
internal
more
or external
at the surface or internal towards the core and the mantle.
Right. Okay. So this book, because it's the second edition, has many forewords. So we're going to start with the author's note, and we'll, like we've done before, next episode I'll read another one, and the next episode I'll read another one. So Einstein's will come next week. But this one is the author's note from Hapgood himself. He says, until a decade ago, the idea that the poles had often changed their positions on the Earth's surface was regarded as extreme, improbable, and unsound. It was advocated strictly by cranks. Nobody who was anybody in the scientific world would have anything to do with it. But fashions change. Today, every other book dealing with Earth sciences devotes space to polar wandering and continental drift. Polar wandering is based on the idea that the outer shell of the Earth shifts about from time to time, moving some continents toward and others away from the poles, changing their climates. Continental drift is based on the idea that the continents move individually. Many scientists have come to the point of accepting both these ideas. The evidence on hand now seems to them to require that the Earth's surface has shifted as a whole and that continents have also changed their positions relative to one another. Up to the present, those who have accepted both ideas have not connected them. They think of them as independent processes acting simultaneously. A few writers have suggested that perhaps continental drift causes polar wandering. But this book advances the notion that polar wandering is primary and causes the displacement of continents. Those geologists who have accepted polar wandering and continental drift, or only continental drift, put the last such change at a long time ago. But this book will present evidence that the last shift of the Earth's crust, or the lithosphere, took place in recent time, at the close of the last ice age, and that it was the cause of the improvement in climate. Two kinds of evidence are responsible for these changing ideas. New knowledge of geomagnetism, or the polarization of the rocks of the Earth's crust by the Earth's magnetic field, has led to the discovery that the poles have changed their places on the surface of the Earth at least 200 times since geological history began. And there is little doubt now, but that when we have the complete list, it will be twice as long or even longer. The other new body of evidence or knowledge has come from new methods of dating events in the past by the use of radioactive isotopes of a number of elements. An isotope of carbon, C14, called radiocarbon, has enabled us to find reliable dates for geological events back to about 65,000 years ago. Isotopes of other elements are good for dating events 200,000 or 300,000 years in the past, and still others date rocks hundreds of millions of years old. With these radioactive dating methods, it has been possible to reconstruct the climatic history of Earth in great detail for the last 100,000 years, and that is what I shall try to do in this book. Some of the results of the chronology of the glacial epoch worked out here are surprising. For example, I have found evidence of 3 different positions of the North Pole in recent time. During the last glaciation in North America, the pole appears to have stood in Hudson Bay, approximately latitude 60 north and longitude 83 degrees west. It seems to have shifted to its present site in the middle of the Arctic Ocean in a gradual motion that began 18,000 or 17,000 years ago and was completed by about 12,000 years ago. The radioactive dating methods further suggest that the pole came to Hudson Bay about 50,000 years ago, having been located before that time in the Greenland Sea, approximately in latitude 73 degrees north and longitude 10 degrees east. 30,000 years earlier, the pole may have been in the Yukon district of Canada. These ideas are new, and they will at first seem strange, but if the reader will plow through the necessary factual detail presented in this book, he may find sufficient proof. So that's the author's foreword. So chapter 1, geomagnetism, continental drift, and polar wandering. Do the poles move? So what do we mean by polar wandering? This phrase may mean several different things. It may be thought to mean a shift in the position of the axis of the Earth. Everyone has seen pictures of the solar system with the Earth, the other planets, and the sun shown in relationship to one another. The Earth is always shown slightly tipped. Its axis does not run straight up and down at right angles to the plane of the sun's equator, but slants at an angle. Any change in this angle, in the position of this axis, would be very important for us. It might mean, for example, that the South Pole would point directly at the sun. We would then have one hot pole and one cold pole. The hot pole would never have any night, and the cold pole would never have any day. The occurrence of this kind of polar shift has seldom been suggested, for the reason that no force capable of shifting the axis has ever been imagined.
But that's not right. Because if it was going around the sun, then it would switch, right? Like if the South Pole was pointed at the sun, then you move the Earth all the way around to the other side of the sun, then the North Pole's pointed at it.
I think that's right, yeah. Yeah, because the axis won't shift.
Unless it was, that would be a really strange type of tidal locking.
Yeah, I don't know. Would it change how this worked? I don't know.
Because that would mean that the pole would be rotating.
Yeah,
itself.
The pole itself would have to rotate
degrees every year.
Yeah.
Which doesn't.
Yeah. So he says this has never been imagined other than possibly a major planetary collision. A second way of shifting the poles would be not to change the direction of the axis, let it point to the same stars as before, but merely to shift the Earth around on its axis so that different places on its surface would be at the poles. This suggestion has also run into difficulties. The main obstacle to such a shift is the stabilizing effect of the equatorial bulge of the Earth. The Earth is not a true sphere, of course, but a slightly flattened spheroid. The polar flattenings are balanced by a bulge at the equator. The diameters of the Earth through the poles and through the equator differ by about 13 miles. The extra mass around the equator, rotating at a very rapid rate, acts like the rim of a gyroscope to keep the Earth steady on its axis. The Earth is not absolutely steady. It wobbles a little. Its off-center path having an average radius of about 50 feet and completing a cycle in 14 months.
What is this again? I'm sorry. My brain
Pay
got
attention,
stuck
Kyle.
on some side paths.
So he's talking about a very slight rotational wobble that happens, and the pole basically
Okay, so like
it has
precession, but it's
but it's fast every 14 months, and it
Okay.
moves in a circle that's about 50 feet in diameter.
okay. All
Yeah.
right, yeah.
But this wobble is not important for us in the present discussion. And then during the 19th century, some of the titans of geology, including James Clerk Maxwell and Sir George Darwin, son of Charles Darwin, considered this problem, and they decided that the stabilizing effect of the equatorial bulge was so great that no conceivable force originating within the Earth could make it shift on its axis. They therefore dismissed the idea of any shift of the poles as impossible and, in fact, not worth discussing. Their influence was sufficient to make sure that nobody until now would seriously consider polar shifts. So on that one, that second example is interesting because he's saying the line of the axis stays the same, but you just kind of rotate the Earth in it so that the whole planet moves, but the axis doesn't change, which is weird.
So not
It seems more likely
not
that
the
you
crust itself, but the entire mass
the
of
entire
planet.
globe, but the axis itself relative to the rest of the solar system
Yeah.
doesn't change. Yeah. That does seem unlikely. It seems to me more likely that the whole axis would roll if something was happening.
Yeah, because you're already getting all the mass in motion in a direction that's not.
Yeah, right.
That's basically it's having to curve from going straight, right? Like
Yeah.
it's got an angular momentum,
Yeah.
so that doesn't make any sense to me either.
Yeah, he's not saying this is what happened. He's just saying here's another way. Yeah.
Right.
A third way to conceive of polar wandering is through the sliding of the Earth's whole outer shell over a semi-liquid layer below. This idea was suggested long ago, like most good ideas, but the fellow who first advanced the notion, Damien something, did not have enough influence to impose the idea on his contemporaries. This theory requires only two things. First, that the material under the Earth's rigid crust, or more properly called the lithosphere, be sufficiently liquid, and second, that there should be available a force sufficient to set the outer shell in motion and keep it moving for considerable distances. Still another way to change the position of the poles relative to the continents is to move the continents. This is now a very popular way of explaining things, and we shall discuss it below. However, first we must ask, what is the evidence that the poles really have changed their positions in one way or another relative to the various parts of the Earth's surface, especially the continents? People have been claiming to have evidence of such changes for 100 years, but only recently have we obtained evidence that really seems indisputable. The new evidence has come from studies of the past history of the Earth's magnetic field. So part 2, the geomagnetic evidence. The magnetic field of the Earth is what influences the compass to point north. The compass needle does this because it is composed of iron, and iron is a magnetic substance, that is, a substance which will itself become magnetic when exposed to a magnetic field, and will therefore align itself with the lines of the force of the Earth's field. What is true of iron in the compass needle is also true of the iron in rocks composed of minerals containing iron. The tiny iron particles in these rocks also take on a magnetization. They become miniature compasses lined up with the Earth's magnetic field. The compass needle, if it is free to move in all directions, vertically as well as horizontally, will start pointing gradually downward as a ship or an airplane bearing the compass approaches the north or south magnetic pole. At the north magnetic pole, its north pointing end will point straight down. And of course, its south seeking end will be pointing straight up, and at the south pole, this would be reversed. At the magnetic equator, the compass needle would lie flat. When iron-bearing rocks have become magnetized, they are actually more informative than a compass. They indicate the direction of north as the ship's compass does, but by the angle of their dip, they also indicate how far away the pole is.
The latitude or whatever.
This means they indicate
cool.
the latitude. The horizontal angle is called variation, and the dip is called inclination. The variation gives the longitude of the sample relative to the present magnetic pole, and the inclination gives the latitude. The magnetic rocks adopt the direction of the Earth's field at the time that they are formed, and in many cases, they preserve their directions of magnetization indefinitely.
This seems so obvious. I'm ashamed that I never thought of that before. That their angle dipping down.
Yeah.
It's like,
Of course.
of course. I blame everyone for not telling me this also.
Yeah, you're right. If you think about it, compasses are they're set up to not be able to move too much up and down. But if you had a fully spherical one, it would point.
Right.
That would, yeah. We need to build one of those. I want my compass in a little glass sphere that hangs from a string. Yeah.
Compass makers, you've been screwing us.
Yes. Why are you giving us these 2D compasses? Of course, there are many problems, Hapgood says. Local movements of the crust may invalidate the evidence by moving the slab of rock containing the sample hundreds of miles along a major fracture, like the San Andreas Fault in California. The sample, through deep burial, might have been subjected to heat and pressure sufficient to destroy its magnetization or to alter the direction of its field. There are other factors that may operate to invalidate a sample, but most of these, however, being local, may be eliminated by the simple means of basing estimates of the position of a pole at a particular time on many samples taken from different places far apart in different countries or continents. He has a couple of maps that he shows here where they're showing pole positions estimated, determined from like European rocks of various eras, late Paleozoic, Mesozoic. So they're showing pole positions on the globe from these different samples. Another problem arises from the fact that the magnetic field of the Earth does not stay put. It is in constant motion, having, for one thing, a steady westward drift. Geophysicists studying this, however, have concluded that over a period of a few thousand years, the Earth's field returns to its original position, and that the average position of the magnetic pole over the whole period will coincide with the Earth's axis of rotation. It is simply a question, then, of taking samples from a rock thick enough to represent the sedimentation of several thousand years. If the sample comes from lava flows, they have to be taken from successive lava flows indicated as having occurred fairly close together in time. When many samples are assembled and the results are averaged to eliminate the errors due to local factors or to the secular variation of the Earth's magnetic field, and when it has become reasonably certain that no factor has intervened to change the original direction of the magnetization, we begin to have a fairly reliable indication of the position of the pole at the time when the rocks were laid down.
Man, this seems like it would be really difficult to do.
Yeah.
Because you're, like, if you're taking a sample back to a lab to figure this out.
You better have some arrows drawn on it.
Yeah. I mean, you have to know, like, okay, here was the exact north-south alignment.
Yeah.
You know, that's, or I guess you could
Test it right there. Yeah.
Or you figure it out in the lab, but you mark it where you can bring it back to the site and somehow have the lines indicated on the sample itself.
I don't know.
This would be a trick to figure this out, to do this right.
Where was I here?
Sorry.
Okay, so if we know approximately when they were laid down, dating them by the included fossils or by one of the methods of absolute dating now available, we can assign a date to this particular pole position. It is obvious from what I have said above that there are traps, so to speak, for the unwary worker in this field. Nevertheless, a vast amount of research has been done, and the state of the science has advanced until we can say that the present findings of pole positions are reasonably reliable. Margins of error are usually allowed. They are indicated by uncertainty ovals drawn around each pole position.
And what time was this that he's writing?
I'm not sure, because it was either be in the late 50s or in the 70s, depending on whether this was correction or not. But he basically wrote this, I guess, in the late 50s or 60s, and then did a new correction in the 70s. Okay. So each of these positions has been found by averaging the directions from many samples in the same geological formation or in geological formations of the same age from other localities. The uncertainty ovals are statistically determined to have 95% accuracy. It is the opinion of specialists that the findings are reliable. What the findings indicate is that the poles have changed their positions relative to the Earth's surface many, many times throughout the history of the Earth.
Very accurate uncertainties.
Yes. Our uncertainties are correct 95% of the time.
That's right.
So
That's good.
that basically saes that it's only a 5% chance that the spot is actually outside the oval, I think, is what it's saying.
I get it. It's just, it's funny.
Yeah. What I'm not understanding here is how he kind of just quickly brushes over the magnetic drift.
Yeah, that they say,
I think one of the ways,
back.
yeah, I think one of the ways that people explain a lot of these pole positions now in the various different, magnetic alignments of different rocks is that the magnetic pole shifts.
Yeah, so it's circular logic.
Yeah.
To say like, well, the pole comes back to where it was because when we look in the ground, like we see that the magnetic grains are like pointing this way and then they're back.
Mm-hmm. I don't know. It just seems like one way you could explain all these different pole spots that he's showing you from different samples is that the magnetic field has drifted around, but
Right.
the actual momentum, the physical pole hasn't moved.
Right.
Because this is all based on magnetic fields.
Right.
But he's saying, well, experts have looked at the magnetic field drift and they've decided that after a couple thousand years, it goes back to where it goes. Anyway, we'll move on and decide that the whole thing is shifting. And I'm just like, okay, you just kind of brushed past that, which is fine. Like, let's pursue this concept of physical pole shifting rather than magnetic one. But I think the common explanation at this point is that it's a magnetic shift, not a physical pole shift, right? That full reversals are explained by a full magnetic pole reversal,
Right.
not a complete 180 degree turn of the entire planet.
Yeah, for sure.
Okay. So it seems obvious that the number of pole positions so far determined, though large, is not nearly enough for any but tentative conclusions about continental drift. The following table illustrates this by giving the average time intervals between the poles so far determined for the different geological periods. I included this because it's an important data point. You guys can't see the table, but there's a table here, and they're showing you Pleistocene, Tertiary, Cretaceous, Jurassic, Triassic, Permian, so on and so forth through all these periods. The average interval between the pole positions that they've determined starts out in the Pleistocene at basically 60,000 years. And then after that, it's 8 million, 7 million, 6 million, 2 million, 3 million, 4 million, 7 million, and then 25 and 33 million. So I think he's trying to say, and this is in average time, right? So what he says is it's obvious that such inequalities in average intervals between polar shifts can have no relation to reality. If there is any regularity, or even approximate regularity, in the intervals between polar shifts, the minimum period indicated in this table is more likely to reflect the truth than are the very long periods. It is perfectly obvious that for very remote geological periods, we have virtually no evidence. For the Pleistocene, it seems we have an average interval of about 70,000 years between polar shifts. I shall show in the following chapters that this may not be very far from the mark. The very long intervals indicated for the older geological periods, I think, reflect merely our lack of information. In this book, I will give special attention to recent geological time, that is, to the Pleistocene epoch. It is commonly thought that no polar shifts could have occurred in this recent period. It is the general impression that the poles have been in their present locations for at least several million years. Magnetic evidence in contradiction of this view, however, now exists. This evidence has resulted from studies of volcanic deposits in Japan by Nagata, Akimoto, and others, and from Soviet studies. The Japanese samples were taken from the Omura-yama group of volcanoes in the North Izu and Hakone volcanic region on the east coast of Honshu. No precise datings of the different lava flows were possible. It is therefore not possible to average out the secular variations of the magnetic pole positions indicated, and they do not necessarily indicate the positions of the geographical poles. In some case, they may indicate the temporary position of the pole at the time of a lava flow when the pole was actually in motion from one position to another. So he shows another graph here where or not a graph, but a table, Pleistocene positions of magnetic North Pole from Japanese samples. Now there's a whole bunch of different positions and they move around quite a bit. And this is all in the Pleistocene. And there are 24 samples. And then he shows another version of the table where he shows that some of them show a complete reversal in the middle of the sample set. Okay. So he says it's interesting to note that table 4 indicates that a complete reversal of the Earth's magnetic field occurred twice during the period. In other words, it reverses once and then reverses again to get back to where it is today. The authors, attempting to interpret the data of this table as a continuous curve, state, quote, on smoothing out the fluctuations whose periods are shorter than the period of each volcanic activity, the position of the North Pole of the geomagnetic centered dipole can be estimated to have shifted from 72 degrees north, 86 degrees east to 81 degrees north, 32 degrees west during the whole Quaternary period. And the Soviet findings, as given in Table 5, are not nearly as complete and their chronological order is uncertain. Nevertheless, they do indicate considerable displacements of the North Magnetic Pole. So I know this is a little bit confusing because you can't see the tables, but the point he's showing is that there's large movements in the Pleistocene, okay, based on 2 different samples from across the world. The geomagnetic data, he says, from older geological periods discussed above have inspired geologists to attempt to construct curves for the path of the pole for tens or hundreds of millions of years. But it seems to me that the evidence is insufficient for the construction of curves in the older periods. It appears that even in the short period of the last million years, such a curve can be constructed only at the cost of sacrificing much of the detail of the evidence. I do not think that those who assume this sort of progressive pole wandering over considerable periods have stopped to work out the logical consequences of their assumption. What does the idea of the curve involve? In the first place, it involves a continuous motion or, in the case of interruptions or standstills, the resumption of the motion in more or less the same direction. Changes of direction would have to be gradual in order to give us the long, smooth curves indicated by the authors of the diagrams. So he's talking about, there's maps you can see where they try to draw these long, smooth curves across the points that they've found.
And we're still talking about the magnetic pole drift here, right? Or is this...
Maybe. They're just showing you where the pole positions are indicated by the magnetic field in the rocks. Yeah.
Yeah.
So is it physical or magnetic?
Yeah.
It isn't clear, but he's just saying, then they draw these smooth curves. But they're supposed to take place over millions of years. And he's saying, are you saying that this is...
When you zoom in, it's like they're going all over the place within that. Yeah.
Or do these people think that it was stopping and starting? And how is it that if that's the case, that it kept stopping and starting and kept moving in the same direction? Yeah. Well, with the forces... So he says changes of direction would have to be gradual in order to give us the long, smooth curves indicated by the authors of the diagrams. And we must remember that if the lithosphere is set in motion over the asthenosphere, immense forces have been involved. A powerful momentum has been transferred to the lithosphere.
So he is talking about actual...
Yeah, he is. Yeah.
Okay.
An equal force will be required to stop it. But stop the lithosphere did, each and every time after a shift, long enough to form the sedimentary rocks that were to become magnetized in the direction of the Earth's magnetic field at the time.
Right.
It is obvious from the methods used in the fieldwork that the polar positions were stable for periods of thousands of years, just as they have been in our day ever since men began to make astronomical records in Egypt and in Babylon.
So that's another thing to consider is that once the sedimentary layers are lithified and the magnetic grains are in that position, they stop being changeable.
Yeah.
So
unless something heats them up again or whatever. Yeah.
Right. So as you go up in the layers of the sediment, you're seeing
more and more recent,
like a gradual motion in one direction or another of either the movement of the land around the magnetic pole or the movement of the magnetic pole around the land.
And it's probably both, right?
Yeah.
Yeah.
Yeah, it's going to be both.
Yeah, and if
I would assume, just based on like recent stuff that like they're clocking the motion of the magnetic pole right now. It's accelerating.
Yeah.
So it's moving faster than the land is right now, but there could be other times when the land is moving faster than the.
What if the magnetic pole is staying in place and it's the other pole that's rolling around? But yeah, I think that's right.
The
magnetic pole shifting around. It's making people have to make adjustments to maps, to GPS readings.
This just brings up another question, which I was trying to look up while you were going through that, which is like, why? I want to know: is there an idea or a reason that the magnetic pole is roughly in the similar position as the geographic pole? I mean, is there a reason that the magnetic pole can't be like at right angles? Because then, like, if you think about it, the Earth is spinning, right? Like it's spinning on its axis. And if the magnetic pole was like shifted far enough down to, closer to a right angle, then that magnetic pole is traveling through the Earth all the time.
Yeah.
So is that why it's because that would be too much resistance? Or I'm just trying to figure out what.
No, it would be. What do you mean it's traveling through the Earth all the time?
Because the mass of the Earth is actually spinning. If the geographic pole was just sitting,
the magnetic pole.
The magnetic pole was like pointed at the equator.
Yeah, so if it was like pointing at somewhere in Mexico or something like that, or Central America,
then it would be spinning around.
Yeah,
with the planet,
right?
Not staying still.
Sure, that's what it's doing right now. It's off center, but it's going around.
Oh yeah, true. Okay, so it is spinning around.
It's over there in the Siberian Sea or whatever, right?
That's right.
I don't know.
So it is rotating.
Watcher, where is the magnetic pole right now? Can you find out? Yeah, it's rotating.
Yeah. If it would,
if it was staying in one place, it'd be really confusing. But yeah.
Yeah. Okay. Right.
Staying in one place relative to
right.
Yeah.
So if it turned to like 90 degree, like a right angle to the geographic pole, then it'd be flipping over itself every day.
Yeah, that would be doing weird stuff because it's in the sun's magnetic field, right? So it's like. That's what I'm saying.
But it's already
what is the source of the magnetic field in the first place? No one really knows.
Well, I got an article here from NASA, so we know that this is true.
No, right.
It's from 2012. But yeah, they just describe it, based on it's like, well, there's this, giant iron ball.
Okay, it's across the straits from Greenland, Nares Strait over Ellesmere Island. Watcher says, thanks, Watcher.
The flow of liquid iron in Earth's core creates electric currents, which in turn create the magnetic field.
Yeah. So does that mean that the flow of the liquid iron is not quite the same as the spin of the planet itself?
It's got to have turbulence in there.
Yeah.
It's not going to be perfect. Right? There's going to be hot spots, cold spots. There's got to be like a random turbulence type of motion.
Yeah.
So the fact that they can say, oh, the pole drifts and then it just comes back to where it was is, I don't know. It seems to me like it would just never actually, like if you were able to
wander around,
if you were able to trace it, it would just be this random wandering that would be as random as the turbulence in the liquid iron.
So what are the reversals then?
I don't know. Shit, bro. Let's take a break.
Okay.
I'll figure it out and then I'll let you know when we get back. Questioning everything you've been told. Not only here, but everywhere. This is Brothers of the Serpent Podcast, a common occurrence.
It is.
Questioning everything we've been told. So, yeah, we were just talking during the break about why the magnetic pole seems to stay aligned roughly with the geographic pole. And it kind of seems to make sense. Like, when you start thinking about a dynamo and it's going to be spinning in the same direction, but I don't know. It's just so, how do we know these things?
Right.
It's a lot of guesswork.
Well, that's what. So I was saying he gets into some geophysics stuff here that we're going to get into, hopefully in this episode and definitely in the next one. That really starts to make you wonder about the interior of the planet. And then, of course, as always with these book reports, you start finding out about the history of discovery.
Yes.
All right. And
good.
Yeah. So here we go. So what is the probability that after the lithosphere has been brought to a halt, with each standstill lasting an unknown and perhaps considerable length of time, that it would resume motion in the same or very, very nearly the same direction? And what sort of force within the Earth could act intermittently in this way? The mechanism I propose to suggest a little later on in this chapter will be one that can account for the starting and stopping of the movements, but it is one that will not act continually in the same direction. According to it, the path of the pole would more likely be a sort of zigzag, with the direction of each new movement determined by the balance of forces within the Earth at the particular time. This zigzag path would tend to ensure the poles remaining within the general area for a considerable time and taking long periods of time to migrate great distances. So there are three possible interpretations of the geomagnetic evidence. We can assume polar wandering, continental drift, or a combination of the two. But in order to be able to see, this is what I'm saying. It seems like there should be four possible interpretations. Polar wandering, unless by polar wandering he means magnetic polar wandering.
Yeah, I don't know.
Right? The interpretation should be the physical pole moves around, or the continental drift. The continental drift does it, which is basically the same thing, but just over a much longer period of time. A combination of the two, or that there's the magnetic pole moving around, or a combination of all three. So he says, but in order to be able to judge...
Well, are you saying polar wandering being the geographic pole wandering is something different than the mass of the Earth moving around? Because that seems to be the same thing to me. How can you have polar wandering if it's a geographic pole without actually also describing it, or more accurately describing it as the moving of the mass of the Earth?
Lithosphere movement, I think, is what he means by polar wandering. Not the whole planet.
Right, sort of like, what people call crustal displacement or something like that.
Yeah. And he separates that from continental drift, because continental drift is just like the sliding around of these pieces.
Yeah. Yeah, and the, subduction zones and what's the other one? Where they're coming out.
Oh.
Forgot the
production zones. I don't know. Yeah. Extrusion, something like that. Those are in the
Watcher.
Those are in the ocean ridges. Okay, so anyway, he says, but in order to be able to judge the relevant evidence, we must, before we proceed, take a look at what is known about the inside of the Earth, where unknown forces have operated to bring these things about. So part 3, a brief survey of the Earth's structure. There is not much that we know about the inside of Earth because we are unfortunately restricted to living on the outside of it. We must deduce what we know from mining and oil drilling activities, seismic waves from earthquakes or artificial explosions, and principles of physics. This subject is wrapped in uncertainty. Therefore, it is natural that there should be differences of opinion, opposing groups of scientists devoted to different notions. However, among the uncertainties, there are some points upon which most scientists are agreed. I will confine myself here to giving, in a condensed form, the consensus of geological opinion on the structure of the Earth. A. There is an outer shell composed of solid crystalline rock about 30 to 40 miles thick, extending down to the melting points of the rocks. This layer is properly called the lithosphere, although it is sometimes called the Earth's crust. B. The lithosphere is theoretically arranged in layers, which include loose sedimentary material on top, then rocks called sedimentary rocks made of such sediments, and then rocks originally made of such sediments which have been melted and partly fused called metamorphic rocks. And generally below these sedimentary and metamorphic rocks are heavier granitic rocks, also partly sedimentary in origin, and finally still heavier basaltic rocks. These layers are not at all uniform in thickness. The layering is only a general tendency. Light rock exists at all depths in the lithosphere, even on the bottom of it, and the lithosphere has been churned up all throughout its history by processes of mountain building and the like. C. At a depth of about 5 miles under the ocean bottoms, and 2 or 3 times that under the continents, there is a discontinuity called the moho, or the Mohorovic, or Mohorovikic, something like that. The moho is the short name for it, that has been much in the news lately. Below this break, the material differs in some ways from the material above, but just how, we do not know. Some scientists believe there is a chemical difference. Others maintain that the difference is only a change of phase. It is, of course, true that heat and pressure can change the appearance, density, and properties of a substance without changing the chemical composition. Everyone knows that graphite, if placed under sufficient pressure and heated, can be turned into diamond. There are some reasons for favoring the phase theory about the moho. For one thing, it would be hard to reconcile a chemical difference at the moho discontinuity with the folding of the lithosphere to its full depth in mountain building. A few years ago, some scientists conceived the idea of boring a hole down to the moho. Congress approved a large appropriation for this operation, and there was hope for an answer to this question of chemical versus phase change. Unfortunately, politics stepped in, and the contract for the operation was taken away from a corporation that was used to oceanographic work and given to a Texas corporation which was less used to working with such problems. Difficulties developed and the project was abandoned. An interesting book, however, has been written about it, and perhaps someday this project will be carried through. The whole question of the moho has produced some unfortunate confusion. Some scientists have fallen into the habit of regarding this discontinuity as the bottom of the crust. The crust used to be regarded as synonymous with the lithosphere, that is, the whole crystalline shell of the Earth extending down to a depth of 30 to 40 miles. This definition has been abandoned. It has become the practice to lump everything below the moho under the general and therefore meaningless term of mantle. Of all the ambiguities in current scientific literature, the confusion of the terms crust and mantle is the worst. It has confused the scientists themselves, as we shall see. One point must be made clear. The moho does not mean the lower limit of the crystalline rock. The rigidity and the strength characteristics of those rocks continue to a much greater depth. This confusion is related to another one concerning with the strength of the lithosphere. Some scientists work from the premise that the lithospheric shell, the outermost shell of the Earth, is weak. They even treat it mathematically as if it were a liquid. This is an error which comes from the failure to distinguish clearly between two different qualities of crystalline rocks, two different kinds of strength. There is tensile strength, but there is also another kind which we may call crushing strength. It is quite true that the rocks of the lithosphere do not have the tensile strength of steel. You could never make I-beams out of rock. It is plain that you can shatter rock with comparative ease. Crushing strength is an entirely different matter. The crushing strengths of rocks differ naturally with chemical composition, but granite and basalt, for example, have enormous crushing strength, as anyone running a car into granite cliffs will discover. The lithosphere, according to Dr. Harold Jeffreys, the Dean of British Geophysicists, is rigid enough to transmit stresses across any distance. We shall see that this crushing strength of the lithosphere, including that part of it that lies under the oceans, will be very important for various aspects of polar wandering and continental drift. I think this is interesting.
I don't know, man. If you have enough logs, you could roll the crust on them.
Yes, that's right. Pyramid building jokes. But this is interesting. This guy, Dr. Harold Jeffreys, says the crust or the lithosphere is rigid enough to transmit stresses across any distance. In other words, you push on any given part of it, and it'll just because it's got great crushing strength or resistance to that kind of movement, will just transmit that stress all the way across the existing rock surface.
Yeah.
Now, obviously, it'll do interesting things when it reaches discontinuities in the rock, but...
So the meaning is, like, let's say you put a piece of granite in a vise,
Yeah.
and you're trying to crush it.
Yeah.
It's the strength of that material to resist crushing.
Yeah, that's right. And to transmit that stress across its body.
Right. Like hydraulics in a way.
Yeah. So what the idea is that you can, if you're pushing on one side of a continent,
Yeah.
you move the whole thing. Now it might,
Right.
it'll fragment. Some things will happen if there's fractures somewhere, but
Yeah. That's where it is. If it's fractured, then you're going to get.
yes, the stresses will get moved around in the fractures. Yeah.
Yeah.
Dispersed across the fractures But
Or,
this is why
or just close them up.
This is why you can drive around and you see these huge forms, right, where it's folded
Yeah.
because there was a fracture there and there's pressures from various, like that might be hundreds of miles away,
Yeah.
pushing on something, and it's caused this place where the fracture is to fold over something else.
Right.
So we shall see that this crushing strength of the lithosphere, including that part of it that lies under the ocean, will be very important for various aspects of polar wandering and continental drift. So it is important to note that the strength of rocks depends on their crystalline structure. The strength of crystals varies with their chemical composition. Ice crystals have very little strength, but granite and basalt crystals are very strong. The rocks of the Earth's crust are composed of billions of tiny, strong crystals that interlock with one another, pointing in all directions, not in neat arrangements. These strong, rigid, interlocking crystals prevent the molecules of the rocks from sliding past one another as they do in liquids. So he's pointing out that treating the crust as a liquid mathematically is
Right.
you can't do it that way.
Slide past each other. Yeah.
So D. Remember, we were going through a letter list.
This is like the same principle that makes steel, the hardening steel, right? If you have like this perfect crystalline structure inside the steel or whatever, it'll shear easily.
Yeah.
But when
You want it mixed up a little bit.
you want it mixed up so that the crystals are all pointing in random different directions.
So it doesn't shatter like glass, basically. Yeah. Yeah.
It makes it more shatterable when you do that.
Oh, okay.
Like tempered steel can break. It doesn't it doesn't bend and flex as easily.
Yeah.
But it's incredibly rigid, right? It's
Okay. So below the lithosphere, there lies a thick layer of rock that is soft, amorphous, and perhaps nearly liquid. This layer begins at the point where the Earth's heat reaches the melting points of the rock, and this is thought to be at a depth of 30 to 40 miles, as already mentioned, both beneath the continents and beneath the ocean basins. This soft layer is called the asthenosphere, from the Greek word for weakness. The evidence for this soft layer is of various kinds. Daly cited geological evidence from mountain building and from the rebound of areas that were depressed under the ice load in Europe during the Ice Age. And Gutenberg calculated that the soft layer extended from 60 to 120 miles down, but this was revised by Anderson to from 35 to 150 miles. And Vauquier has pointed out that magnetic anomalies showing strike-slip displacements of the ocean floor suggest a soft layer underneath. The existence of displacements in the ocean floor of magnitudes comparable to the distances that continents are presumed to have drifted indicates that there must be a mechanism for lubricating, so to speak, these displacements, so that whole continents, and in the present case, stretches of oceanic crust several hundred kilometers long, remain virtually undistorted by this motion. So that's interesting. He's saying, you have to, somehow you've got to move all this stuff in like an enormous amount of material and sometimes at very long distances and leave them basically undistorted by this motion.
Yeah, except at the edges.
Yeah. Chadwick presents various arguments for the existence of the soft layer. This soft material of the asthenosphere may be technically a liquid, but that doesn't mean that it is as liquid as water. It may be more like a stiff tar. The difference is a matter of viscosity. The viscosity of a liquid is its resistance to flow. Water has low viscosity. Melted rock as we see it, for example, in lava flows, has higher viscosity. It is true also that pressure increases viscosity because it presses molecules more closely together and makes it harder for them to flow past one another. The asthenosphere, then, may be fairly stiff even right below the lower limit of the lithosphere, and probably grows stiffer with depth, even though the heat, which is also assumed to increase with depth, tends to counteract the effects of pressure by reducing the viscosity. So the heat grows, which would thin it out, but the pressure also grows, which keeps it at high viscosity, is what he's saying. Studies of the velocity of earthquake waves suggest that the viscosity increases in the lower levels of the asthenosphere until at a depth of 180 to 250 miles, the material may behave in some respects like a solid. Again, we shall find all of these facts vital in evaluating theories of polar wandering and continental drift. There are still other factors to be considered with respect to the asthenosphere, which, as we have just seen, in its lower parts may not be weak at all. So far as viscosity is concerned, chemical composition is just about as important as heat. Each chemical substance has its own melting point, its own degree of viscosity under the opposing influences of heat and pressure. This makes it impossible to be sure exactly where the lithosphere ends and the asthenosphere begins, or to know what the viscosity of the asthenosphere is. Such information is not at present available, though there are some indications. We can make deductions from some lava flows as to the chemistry at the bottom of the lithosphere, but unfortunately lava flows differ in chemistry. Dr. Reginald Daly of Harvard reasoned that the asthenosphere right under the bottom of the lithosphere had to be virtually a liquid to account for the easy response of the lithosphere to the growth and melting of ice caps. So in other words, the amount of isostasy that they see under the ice caps implies that at least right below the lithosphere, the asthenosphere must be very low viscosity. Mm-hmm. In other words, easily respondable to being depressed. As if the situation were not already difficult enough, it appears that two other qualities of matter must be taken into account. One of these we call plasticity, and the other, already mentioned, is change of phase. The term plastic is often used these days by writers on geophysics as if it were synonymous with viscosity. But the plastic behavior of rocks has nothing whatever to do with viscosity. It is, in fact, an opposite kind of behavior. The difference between them is all important for the issues that we are discussing. The difference between them is that if you apply pressure to a viscous material, it will yield gradually at a speed proportional to the pressure applied. Therefore, with twice the pressure, the material will yield twice as fast. Plastic deformation works differently. Every chemical solid has a plastic limit. It will behave like a solid until the pressure reaches that limit. Then it yields suddenly and completely. It does not yield at a rate proportional to the applied force. It is almost like the breaking of the branch of a tree. When the branch breaks, its strength is suddenly and entirely gone.
Yeah.
So that's interesting. So viscosity, you press into it and it just moves out of the way at a rate that's relevant to the pressure. But with plastic, it acts like a solid until you increase the pressure beyond its plastic limit, and then it just moves.
Yeah.
Quickly. It reaches a limit. That's very interesting. So this type of plastic behavior deep in the earth permits very sudden events to take place at a level where the viscosity is very high. According to Daly, who based his opinion on laboratory experiments carried out at Harvard, this is the true explanation of deep focus earthquakes. So that's also interesting.
Like suddenly it reaches that threshold.
And then a bunch of stuff moves very quickly, and then you got a deep focus.
And then you get all the repercussions, the waves from that vibration moving out, tearing everything up. Wow. That's cool.
So completely unlike viscosity, the plastic strength of materials decreases steadily with increasing pressure. It therefore reaches a low point in the bottom levels of the asthenosphere, and this permits the fracture and slip of materials under great pressure, as were observed in the above-mentioned experiments in the laboratories at Harvard. Some scientific writers, failing to take into account the plastic behavior of materials, have made the error of assuming that the deep focus earthquakes mean that the crystalline structure of the lithosphere extends to depths of 300 to 430 miles, an impossibility unless the intensity of the Earth's heat at these depths has been grossly exaggerated. The Earth's heat, unfortunately, is another mystery. Formerly, it was thought that it originated with the planet and was greatest in the core. Now it is thought that most of the heat originates from the decay of radioactive materials in the lithosphere, and very little of it comes from greater depths.
Wow.
We have no direct evidence that can settle this matter. It is quite possible that the heat gradient we observe in deep mines, on which our estimates are based, does not extend all the way to the Earth's center. If that is true, it will pull the rug out from many of our ideas. Okay, part E. Remember, again, we're going through a lettered list. It's just very long parts. This is E.
Okay.
In addition to these various uncertainties, we must also consider change of phase. As already noted in the case of
That's
the
what I've been
MOHO,
thinking about.
a chemical substance under different conditions of heat and pressure may change state. It may expand or contract, or a change of phase may permit it to enter into chemical reactions with other minerals which could not have occurred in its original state. It seems that such a layer has been discovered in the asthenosphere at a depth of about 100 miles. According to the Soviet geophysicist V.V. Belousov, chemical processes at this depth, made possible by a change of phase, are changing heavier into lighter rock, thus causing gravitational instability as the lighter rock tries to rise to the surface. Belousov has named this the waveguide layer. Observations by the American geophysicist Frank Press are in general agreement. Press finds from satellite observations that this layer is a very liquid layer, and it seems that if the Earth's outer shell does slide as a unit over the interior, this is the most likely level at which this movement can occur.
Yeah, I was thinking about.
Of course, the guy's name is Press.
Are you serious?
Yes, Frank Press.
I was thinking about the, like ice skates, right? Like the ice skating. So you have a phase change that happens under the pressure and heat of the blade.
Yeah.
And so then you're like gliding, and it
Yeah.
seems extremely low friction, right? Because there's a tiny little layer of liquid water right underneath that blade,
Right.
created by the heat and pressure. So if you stand still long enough on the skates, then it can cool down and refreeze.
Yeah. Or if it's like minus 50 degrees, you may not be able to skate very easily. I wonder what temperature it has to get down to make ice skating basically impossible. Where you're just scraping along.
Yeah, it'd be the same as scraping along on concrete or something.
Yeah.
That would be really low, probably.
Okay. F. Now we're at part F.
Yeah.
Below the waveguide layer, the material continues to increase in viscosity because of the increasing pressure until it reaches the state that Professor Daly referred to as a pressure solid. Below this point, at a depth of about 430 miles, earthquakes do not occur. It would seem that here viscosity has finally conquered plasticity. The exact depth at which the pressure solid begins is uncertain, but it is vital for the various issues involved in continental drift. So it at that point, it almost doesn't matter how plastic the material is or what it's the pressure so high that it just
Doesn't move.
it doesn't. Yeah, it acts like a solid.
That's crazy. We were thinking, we've been talking about the nuclear fusion, and it's like these pressures way down there are still not enough
Yeah.
to push these atoms together, like the nuclear of these atoms.
Not even close. Yeah.
It's crazy.
Yeah. I wonder about this source of the heat. There's always this assumption that the deeper you go, the hotter it gets. But if the source of the slowly increasing heat that is detected in deep mines and boreholes and stuff like he was talking about is actually a buildup of the of radioactive decay of stuff that does it continue into the depths.
Couldn't it also be the heat, like residual heat from the actual slipping and the friction and motion of the crust itself?
I thought friction was a big part of this, but I guess because they don't even mention it.
You can, once you get to that layer where it's the pressure has overcome viscosity and plasticity, then maybe it's much cooler there.
Could be,
or at least it may be hot at that area, and then the deeper you go, it's actually cooler. Yeah, because it's away from all of that motion and friction.
Yeah. It's also very insulated, so any heat was there, it would just sort of stay for a long time.
Right.
Yeah.
Well, that's what I was thinking too about the mines. It's like the deeper you go, the closer you get to the mantle. I don't want to use that anymore, but
the bottom of the lithosphere.
Yeah, the bottom of the lithosphere, where all this slippage is happening, you're going to have like a lot of residual heat from all of that friction.
And I wonder if that's true all the time. If it's true that no matter where you are, the deeper, like if you're cutting really deep, it just keeps getting hotter and hotter, and what the source of that heat really is. Okay, part G. Finally, at a depth estimated at 1,800 miles, we arrive at the Earth's core. And remember that all of this is him describing and then also commenting on basically the consensus of the interior of the planet.
Yeah. In the 1970s.
Yeah. At a depth estimated at 1,800 miles, we arrive at the Earth's core, containing, according to some experts, 2 layers. And this is weird. An outer one, which is solid, and an innermost one, which is liquid. I think it's the opposite. Now, I've always heard that the outer layer is liquid and the inner one is solid. So has that changed, or did he get this wrong? The innermost core may or may not be an iron core. There may or may not be rapid currents in it.
Yes, you're right. Look, it says right here, this is the NASA 2012. Geophysicists are pretty sure that the reason Earth has a magnetic field is because its solid iron core is surrounded by a fluid ocean of hot liquid metal.
Right. So I wonder if in the 70s or earlier it was reversed, or if he just got this wrong. I don't know. Because he says an outer one which is solid and an innermost one which is liquid. The innermost core may or may not be an iron core. There may or may not be rapid currents in it. It may or may not have any connection with the Earth's magnetic field. If we discuss these questions, it is only to present differing views. There is no consensus.
Oh, wow. The watcher says at negative 22 degrees Fahrenheit, skating on ice becomes almost impossible.
Ice temperature, not air temperature.
Ice temperature.
Okay. I didn't think you'd have to go that far down.
So the heat and pressure of the skate doesn't work. You'd have to have heated skates.
Heated skates. Yeah, or be a very heavy person.
Be going really fast.
Yeah, going really fast. All right. Part 4, continental drift. The theory of Alfred Wegener. It looks like Wegener, but I think it's...
I would think that would be Wegener.
Yeah.
If it's German, it's...
Yeah. I did look it up. I think it's supposed to be like Wegener or Wegener. Anyway, Alfred, who first drew attention to the idea of continental drift, was a good scientist, but he was not a geologist. He had found quantities of evidence of fossil flora and fauna that could not, in his opinion, be reconciled with the present positions of the poles, inasmuch as the authorities such as George Darwin and Maxwell forbade any thought that the axis had moved or that the Earth had shifted on its axis. Wegener suggested that the continents had moved.
If it would only be Wieg if it was
Is it
I-E.
Wegener?
Yeah.
Okay.
Sorry.
That's all right. I did look this up. This is how they show to pronounce it.
So that's Wegener.
Wegener.
Unless
Yeah.
I mean,
Okay. That's a good way to say it.
that's weird because it's just E. I don't know. But go ahead.
Watcher, help us out. Okay, so Wegener imagined that is that what part I was reading? Yeah, okay, so he suggested that the continents had moved. This would have precisely the same effect as polar shift, for it would mean that at different times, the same areas might be found in very different latitudes. Wegener imagined that the continents, formed of light sedimentary and granitic rocks, were floating in the heavier basaltic material of the ocean bottoms. He thought he saw evidence in the shapes of the continents that they had once formed a single mass, which had split so that pieces could go drifting off over the ocean bottoms.
Yeah, something that every child notices as well.
Yeah.
When they look at a globe.
He thought of the ocean bottoms as composed of soft, amorphous, or viscous rock. From a vast amount of fossil evidence from the plant and animal life of the past, he imagined that he could reconstruct the paths of the continents over long periods of time, and he proposed to explain the mystery of ice ages by this theory. He suggested that during the last ice age in the northern hemisphere, Europe and America had lain together near the North Pole, but that since then they had drifted away from the pole and each other. Wegener's theory had great appeal, not because all the evidence supported it, not because the authorities were open-minded about it, not because its mechanics were very plausible, but because it was the only theory that at the time could make sense of the evidence of the fossil flora and fauna. A number of weaknesses in this theory were gradually revealed. As knowledge of the ocean bottoms increased, it was discovered that the rock under the oceans, which Wegener thought to be plastic enough for the continents to drift over, were in fact very rigid, and indeed stronger than the rocks of the continents. This meant that the continents could not drift without displacing and pushing to one side a layer of rigid rock estimated to be 20 miles thick. It therefore seemed to be impossible for continents to drift. Jeffreys, basing his opinion on the evidence for a rigid and comparatively strong ocean floor, said, quote, "There is therefore not the slightest reason to believe that bodily displacement of continents through the lithosphere are possible," unquote. And the geophysicist F.A. Venning, according to Umgrove, conclusively proved the considerable strength of the crust under the Pacific.
All right.
Yep.
Take a break.
Take a break. There's much more to come. We are back, ladies and gentlemen. Second half of the show, Brothers of the Serpent podcast. Continuing on with our first episode of the Path of the Pole book report by Charles Hapgood. So continuing on with he's discussing continental drift, and we had a discussion on the pronunciation of this name, Wegener. Is that what we decided?
Wegener. Yeah.
Wegener.
That's. I think that's right.
Okay. So another weakness that appeared in the Wegener theory was in its assumption that the ocean bottoms were smooth plains. This assumption seemed necessary to the theory, for otherwise the continents could hardly drift over them. However, as the result of the oceanographic work of recent years, it has been discovered that there are mountain ranges on the bottoms of all the oceans, and that some of these ranges are comparable to the greatest ranges on land. Furthermore, several hundred volcanic mountains have been discovered spread singly over the ocean bottoms, many of them of great age, others comparatively young. The Wegener theory involved the corollary that, as the continents had drifted very slowly over the smooth ocean floors, these floors would have accumulated sediment to great thicknesses. It was thought that the sediment laid down in the sea behind the moving continents would provide an unbroken record of life from the beginning of the geological record. However, the greatest surprise of recent oceanographic exploration has been the discovery that this supposed thick layer of sediment is non-existent. The layer of sediment on the ocean bottom is uneven, in some places only a few feet or a few inches thick, and is rarely of great thickness. I think this is a very interesting problem. So it's like you're like, is it currents pushing it around? Is it like ocean impacts throwing it up on land? Like, why isn't there enormous amounts of deep sediment at the bottom of these oceans? What keeps cleaning it out of there?
Yeah, or they're just not that old.
Right. Another startling contradiction to the original Wegener theory is presented by recent data that have drastically changed our ideas regarding the date of the last ice age in North America. We have learned through the new technique of radiocarbon dating that this ice age ended only 10,000 years ago. In Wegener's time, it was considered by geologists to have ended several times that long ago. Since Wegener supposed that Europe and North America had been situated close together and not far from the pole during the Ice Age, this new data have the effect of requiring an incredible rate of continental drift. 3,000 miles of drift in 10,000 years would amount to 1,500 feet a year. Furthermore, movement at something like this rate would have to be still going on, for the momentum of a continent in motion would be tremendous. And what would be the consequence of movement continuing at this rate? It would mean that oceanic charts would have to be revised every few years, while transatlantic cables would be breaking all the time.
Yes.
To cap the case, Gutenberg has shown that the various forces that Wegener depended on to move the continents are either non-existent or insufficient, while another geophysicist, Lambert, has stated that they amount to only 1/1,000,000th of what would be required. Despite the apparently overwhelming character of these objections, attempts to rehabilitate the Wegener theory continued. Daly attempted to find a better source of energy for moving the continents. Hansen suggested that the centrifugal effects of ice caps might have moved the continents. A contemporary Soviet plant geographer, while recognizing the objections to the theory, nevertheless remarked of it that, quote, "It constitutes the only plausible working hypothesis upon which the historical plant geographer can base his conclusions," unquote. As recently as 1950, the British Association for the Advancement of Science divided about equally by vote for and against the Wegener theory. The difficulties with Wegener's concept of continental drift forced people to explore other possibilities of shifting the poles. The British astronomer Thomas Gold postulated that the Earth's wobble on its axis could cause plastic readjustments of its mantle, sufficient to move the poles 90 degrees in 1,000,000 years. The French geographer Jacques Blanchard suggested the possibility of extensive polar shifts due to more pronounced wobbling of the Earth in the past. And Professor Ting-Ying H. Ma of the National University at Taiwan suggested a combination of continental drift with displacement of the outer shells of the Earth down to a depth of several hundred miles. And Bain thought of displacements of the lithosphere to account for the facts of ancient plant geography and fossil soils, and suggested a mechanism to account for them. And Pauly revived a suggestion made by Eddington that the lithosphere may have been displaced by the effects of tidal friction. And Kelly, in a provocative work on collision geology entitled Target Earth, offered the hypothesis of displacements of the lithosphere as the result of collisions with large planetoids. Recently, Monsina and Smiley have suggested that great earthquakes may have had the effect of shifting the poles. So you can see he's going through this list here of all these different ideas. Some of them sound familiar.
But the last one, it would seem that great earthquakes might be the result of the shifting of the poles, as opposed to the cause.
Yeah.
Right.
Yeah. Can they be both?
I mean, I guess.
Pole shifts for some reason that causes great earthquakes. Great earthquakes happen in the pole shifts.
Yeah. Yeah. In other words, there's still some other force that's causing the earthquakes.
Yeah.
Right. So there's some force that's causing the mass of the Earth to want to move, and then that causes vibration across the crust, which is earthquakes. And that's the way I look at it. You know what I'm saying?
Yes. Okay. Continental drift, the new theory. So none of these ideas was taken seriously until the development of the evidence of terrestrial magnetism. Then people began to take a new look at the theory of continental drift. Since changes in the positions of the poles relative to the continents now apparently had to be accepted, perhaps continental drift would provide a less sensational way out than displacements of the entire lithosphere. It is quite true that the geomagnetic evidence very early indicated clearly that at the very least, both things had happened. Nevertheless, such is the frailty of the human mind, scientific or not, that displacements of the lithosphere have been pushed far into the background and all the attention has been paid to continental drift. Nothing has been done to develop the consequences or implications of polar shift, while on the other hand, a large amount of research has gone into explaining how continental drift could have occurred. The most vital problem, if the continental drift theory was to be resuscitated, was to find an adequate source of power to move the continents. Professor J. Tuzo Wilson, together with others, proposed such a source. They suggested that the continents could be moved by the operation of powerful currents under the lithosphere, powered by convection cells formed in what they call the mantle, and we call the asthenosphere. A convection current is set in motion in a liquid by a source of heat situated at some depth and concentrated more or less at some point. A Bunsen burner under a beaker of water will illustrate the principle. The heat is concentrated at some point under the beaker. It heats the water immediately above, which expands and rises to the surface. At the same time, water begins to sink to take place of the rising water, and the rising water reaches the surface and flows horizontally to the point to where the water is moving downwards, and so a circular convection cell is created. Anyone can see a convection cell of this sort in operation if he throws a spoonful of cornmeal into a pan of boiling water. Mr. Wilson and other geophysicists now argue that when a convection current in the mantle rises under the crust and spreads out in opposite directions, it will tend to pull the crust apart. There will be a drag on the undersurface of the crust. Then, when the current arrives at the place where it will descend again into the earth, it will tend to pull down and fold the crust over it. The effect is that a whole section of the crust has been moved laterally. The speeds of such currents have been estimated at from 1 to 4 centimeters or 1.5 inches per year. It is obvious that if such a movement should continue for a few 100 million years, continents could be moved a long way. At this point, the confusion of terminology already mentioned becomes serious. When some writers speak of currents rising under the crust, they mean the lithosphere, but others mean the moho. And there is a tendency to forget all about the fact that the strong, rigid, crystalline rocks of the lithosphere extend down some 40 to 45 miles under continents and oceans alike. There is a tendency to think of the viscous mantle, or the asthenosphere, as coming right up to the moho, only some 5 miles below the bottoms of the oceans. These writers even go so far as to include the ocean bottoms themselves, which of course are part of the rigid lithosphere. We shall examine a notable example of this confusion below. And there are some rather serious difficulties with the convection current idea. It is not that much doubt exists that convection currents, or some kind of currents, do operate below the lithosphere. It is a question of the scale on which they can operate and of their ability to satisfy the complex requirements of the evidence. The first problem is the motive power, the radioactive heat. In order to move whole continents, the convection currents would have to have amplitude. They must rise from the very bottom of the mantle, not far above its boundary with the core, and when they reach the bottom of the lithosphere, they must flow horizontally for thousands of miles. The source of power for this motion is supposed to be radioactive heat, but it has been learned, and the matter is not in dispute, it is part of the consensus, that most of the radioactive materials in the Earth are confined to the outer 40 miles of it, i.e. to the lithosphere. Most of the heat from the radioactivity is believed to be generated there. Logically, the lithosphere ought to be nearly as hot as the bottom of the mantle. It would seem strange that the convection currents should be bringing up heat to the lithosphere when it is in the lithosphere itself that most of the heat is developed.
Why are these heavy metals, these radioactive materials, on the surface?
I don't know.
It seems like they should be way down in the...
I agree. He's pointing out that this is part of the consensus, not that necessarily that he agrees with it. He's like, the consensus about how the Earth's interior is constructed is basically saying that the source of the radioactive heat is the lithosphere, not farther down below it.
That's weird.
But yeah, you would think that these heavy metals should end up deeper, but I don't know. So, okay.
I guess that's more based on the idea of like we're the crust on top of a giant liquid lake where heavy things can sink. But if it's if it's really rigid and hard down there, then
that's
won't.
true. Yeah. So even if we allow that some localized heating in depth may produce convection currents, still this concentration of most of the radioactive heat in the lithosphere does most certainly remove much potential power and therefore amplitude from the convection currents. Another factor militates against convection cells. We have seen in our review of the Earth's structure that viscosity increases with pressure until, at a certain depth, the material of the Earth is thought to assume a pressure solid state. This situation develops long before the core is reached. It is not probable that convection currents can operate significantly in a pressure solid. It is therefore unlikely that convection cells can develop the amplitude necessary to move continents. A recent writer on this subject, Norman H. Sleep, has remarked that failure to take the effects of viscosity into consideration tends to vitiate much thinking about convection currents. A laboratory experiment constructed by T.D. Foster has demonstrated that high viscosity in a liquid inhibits convection circulation and reduces the amplitudes of the convection cells. So now I ask, what is the sense of using one term, mantle, for a series of shells that includes part of the rigid lithosphere below the MOHO, the weak shell of the asthenosphere, the chemically active waveguide layer, and the pressure solid shell down to the boundary of the core? Let us be careful not to be confused by it ourselves.
So, but going back to the question about heavy metals falling to the bottom, how is there an iron core then?
Yeah.
I mean, I don't know. That's strange.
I don't know. It does seem weird that you're basically saying, well, you've got, you basically got molten rock, and then down in the middle, there's just metal.
Yeah.
It's like a big ball of metal surrounded by really hot rock. And then in the surface, it's all mixed up. There's heavy metals.
Yeah, how do they get into the surface?
I don't know.
Electric universe.
Yes. And they get there in these wavy,
there's got to be
strange-
some.
Yeah.
It's. I mean, when you think of like the idea that it was this big molten ball in the early stages,
Yeah.
then you can imagine, all the heavy stuff can fall to the center.
Yeah.
But if it's so pressurized down there that it's basically a solid,
Yeah.
then whatever's there at the time that it solidifies, in other words, that its motion slows to the point that it can basically assume the pressure solid state.
Yeah. You need to start with an iron ball to do that.
Or at least while it's in motion, you have enough time to accumulate heavy metals in the center, and then you get the pressure solid once it's what is it, kinetic energy, like its motion energy slows to a point where it can get, now it's got this pressure solid where no more heavy metals can fall through that. Maybe. I don't know. I'm trying to work it out. It's not working.
And I think that these are, a lot of this is like you're describing an enormous amount of stuff. So to say that there's no radioactive materials down there is that's probably not what they really mean. There is just not enough to
not in abundance.
Heat.
Yeah.
Stuff.
Okay.
So now we come to another difficulty. The rising convection current comes up under the lithosphere, not the MOHO discontinuity, and it shears out, as they say, under it. Remember that the rigid shell of the lithosphere is 30 to 40 miles thick. Do you believe that this current of viscous rock moving gently under it can tear it apart? Do you believe that having torn it apart and having moved it a few hundred or a few thousand miles, this current can then pull the lithosphere down into the Earth's depths, folding it? This sounds extremely improbable to me. Okay, part 6, the hypothesis, according to Dietz. A contemporary scientist who has taken a leading part in the development of the present theory of continental drift is Robert S. Dietz. He has simplified our task of presenting his ideas by very clearly defining his assumptions and postulates. He also states that they should be regarded as tentative and suggestive rather than final in any sense of the word. To start with, he gives us his basic assumptions. Statement number 1. Large-scale thermal convection currents, fueled by the decay of radioactive materials, do operate in the mantle, and they do provide the primary diastrophic forces affecting the lithosphere. So we can take this first statement to mean that he ascribes the formation of mountain chains and other features of the Earth's surface in the last analysis to these convection currents. He then defines the Earth's outer shell as follows. Statement number 2. It is relevant to speak of the strength and rigidity of the Earth's outer shell. The term crust has been effectively preempted from its classical meaning by seismological usage, applying it to the layer above the moho. For considerations of convective creep and tectonic yielding, we must refer to a lithosphere and an asthenosphere. Deviations from isostasy prove that approximately the 70 outer kilometers of the Earth, under the continents and oceans alike, is moderately strong and rigid, even over time spans of 100,000 years or more. This outer rind is the lithosphere. Beneath lies the asthenosphere, separated from the lithosphere by the level of no strain or isopiestic level, or isopiestic. I don't know how to say that word. And I actually looked it up and did not get I got no results. So I don't know what that word is. isopiestic. So this is a domain of rock plasticity and flowage where any stresses are quickly removed. If convection currents are operating subcrustally, as is commonly written, they would be expected to shear below the lithosphere and not beneath the crust, as this term is now used. So, Hapgood says, it seems clear from the above passage that Dietz accepts the views I have presented in the consensus as to the strength and rigidity of the lithosphere and its thickness of about 30 to 40 miles. And he even points out himself that the convection currents would shear beneath the lithosphere and not invade it. Then he makes a statement that appears to be in total contradiction to all of this. Statement number 3. In summary, the model proposed here is that the mantle is ultramafic or perioditic, or composed of heavy rock. The continents are buoyant rafts of sialic scum. The seafloor is essentially the exposed mantle of the Earth, covered only by an oceanic rind. That's really interesting. So the seafloor is exposed mantle, just covered by a thin...
Oh.
Since the seafloor is fully invaded by the convection currents and convection circulation, the term oceanic crust is a misnomer. So Hapgood says it seems that in statement number 2, he allows for the existence of the lithosphere, but in statement number 3, he disregards it. In statement number 2, we have a rigid Earth shell possessing some strength extending down 30 to 40 miles under both oceans and continents, while in statement number 3, we have the convection current invading the seafloor itself, and he makes his meaning very explicit in statement number 4. Owing to the small strength of the lithosphere and the gradual transition in rigidity between it and the asthenosphere, the lithosphere is not a boundary to convection circulation, and neither is the moho beneath the oceans, because this is not a density boundary, but simply a hydration of the mantle substance itself. Thus, the oceanic rind is almost wholly coupled with the convective overturn of the mantle creeping at a rate of a fraction of a centimeter a year to as much as 1 to 2 centimeters per year. Since the seafloor is covered by only a thin veneer of sediments with some mixed in, it is essentially an outcropping mantle. So the seafloor marks the tops of large convection cells and slowly spreads from zones of divergence to those of convergence. These cells have dimensions of several thousands of kilometers. Some cells are quite active now, while others are dead or dormant, and they have changed position with geological time, causing new tectonic patterns.
Wow, that's cool.
Yeah, it is really cool. Okay, Watcher says isopiestic.
But what does it mean?
What does it mean?
So if the ocean floor is completely subjected to this convection turning,
Yeah, he's actually saying that it's actually a part of it.
Yeah, it's part of it, right?
Yeah.
So that's we see these subduction and abduction zones or whatever are just that pattern of convection overturning. So what's happening under the continents then? Like that's actually sliding underneath the continents?
Yeah, it pulls it down at the other end. This is the other part that they
Or
get
are
into.
the continents but the continents, so what is he saying the continents aren't like rigidly attached to that thing that like that the ocean floors basically can slide underneath the continents
I think so.
and drag them along?
Yeah.
So we should be able to see that somewhere, right? I mean, that it seems like.
Yeah, he gets into more of this too. It's like at the there's a chain of mountains along the west coast of the American continent, North and South American continent, but that's actually the exception. You know, that there aren't mountain chains at the edges of the ocean basins in most places on the earth on coastlines. So, where is the subduction happening? This is the other problem is where is it going back down?
So it could be where the mountains are. Like
Could
there's
be.
way down under there, it's going down, but it's dragging against the continent itself, and so it's causing this,
crumbling
wrinkle.
Yeah. But remember that this is also this guy's standard model statement. He's trying to explain how it's working. Yeah.
Yeah, I'm trying to figure out how his idea works.
Well, Hapgood's got a problem with it already because he's like the guy's trying to have it both ways.
Yeah.
He's giving you an explanation for how the convection currents work using, very thick crusts all over the place.
Right.
And then says that the movement occurs because the crust is actually really thin under the oceans.
Mm-hmm.
That it's actually, that the convection currents actually penetrates.
All the way through.
Up into
the ocean.
up into the ocean floor. And that's how it can exert enough pressure on. And, because it's like if you have something sitting on something that's stabilized by a bunch of stuff around it, and there's a convection current on it, it might move around a little bit, but the convection current can't drag it around without it being free to move.
Mm-hmm.
Right. But if the convection current was actually going up and penetrating into it, then it would have much more force to be able to sort of push it around.
So isopiistic is of
Relating to
equal pressure.
Yeah. Okay. Isopiistic. And then, there were a couple other words he used in here that were weird. But anyway. Okay. So Dietz appears to have accomplished the feat of adopting two opposite positions simultaneously. His suggestion of a gradual transition between lithosphere and asthenosphere can be accepted only in a limited sense. The strength resulting from crystalline structure in the lithosphere will be essentially unmodified until, with increasing depth, the heat reaches the melting point of the rocks. Then the crystalline structure will disappear, and the rocks will become viscous and weak, and we have the asthenosphere. The transition cannot be gradual in the sense that it is continuous from the top to the bottom of the lithosphere. It must be comparatively sudden, with variations from place to place because of variations in heat and in the chemical composition of materials, which, of course, have different melting points. But these variations would average out within a range, let us guess, of about 6 miles. That, at least, seems reasonable to me.
6 miles below. Oh, within 6 miles of each other? Yeah.
An average of 6 miles is where this phase change takes place.
Yeah, that's what I was going to say, too, is that it doesn't seem it would be gradual because phase changes are very specific. There's thresholds.
But they're also very specific to chemical composition plus heat and pressure.
Right.
So if that varies, then, it's...
Yeah, but so it's going to be lumpy.
Yeah.
But the idea that in any given area, it's going to be like this slow...
Yeah, no, it's going to be sudden.
Yeah.
But a 6 mile tall lump is a big lump.
Right.
That does give currents things to push on. I
Right,
think.
for sure.
Yeah.
Yeah. You got to go uphill or downhill someplace. Yeah. Yeah, it's like...
think of a mountain 6 miles tall. We don't have one, but there would be a big mountain. If it was extending down into the asthenosphere for whatever reason.
Right.
Okay.
It's grippy when it's lumpy.
Yes. So seafloor spreading. Fortunately for the resurrected continental drift theory, new discoveries have suggested a way out of the dilemma presented by Dietz. A few years ago, a great system of fissures, or canyons, was discovered in the Atlantic Ocean, running down the crest of the Mid-Atlantic Ridge. As the progress of oceanographic exploration revealed the extension of this ridge to all the oceans, it also revealed that the system of fissures was worldwide, and it has been charted for a length of 40,000 miles. The worldwide mid-oceanic ridge is a belt of mountain ranges several hundred miles wide, many of the ranges rising to heights under the sea of 2 miles or more. It has been found that the rocks of the ridge are of recent origin as compared with the rocks of the ocean floor on each side of the ridge. It seems that islands in the Atlantic are geologically older the farther they are from the ridge. The astonishing conclusion appears to be that magma, heavy basaltic molten rock, is continuously or perhaps periodically welling up through the 40,000-mile-long oceanic fissure, thus creating new ocean bottom and spreading the ocean floor. The sea bottom on each side of the ridge is being pushed away, and therefore the continents are being pushed apart. The Atlantic Ocean is therefore a rift ocean, created by the pushing apart of the continents. At the present time, it is still believed that the seafloor spreading process is powered by convection currents. It is possible that convection currents are entirely unnecessary as a mechanism to cause seafloor spreading. There may be quite a different way to account for the facts. But before we consider this alternative possibility, there are some other matters that demand attention. The oceanographer Bruce Hezin has discovered a number of serious difficulties with the ocean floor spreading hypothesis. And we're almost out of time here. So probably should stop before I start diving into this next big section. We won't be able to finish.
Yeah, but what's the big problem? Just the main problem.
Well, you'll have to wait till the next episode to find out. Well, the first thing he says, I can tell you, is that in most cases off the coasts of the continents, there isn't like a gradual sloping down into the depths of the ocean, but you get out so far and then it just drops off like a sheer cliff on all sides. And this is a problem. So that's the first part. It's a long, complicated thing, but that one's interesting.
Something wrong with the earth. No, that's really cool, man. Fascinating stuff. All right.
Yep.
How many episodes is it going to take to get through this book?
Well,
you didn't get through everything you marked, obviously.
No, but we're 10% into the book. And as always happens with these book reports, in the beginning, we're reading a lot of stuff.
Yeah.
And as we get through it, we can skip more and more. But in the beginning, you need all of the setup material.
Yeah, for sure.
So we made it 10% of the way through. If I kept reading as much as I've been reading, it would take 10 episodes, I guess.
Yeah, but there are a bunch of sources and stuff, materials at the end?
Yeah, if there's not a 20% amount of book sources at the end. But we'll be skipping more later. So I think maybe 5, 6.
Cool. I love it, man. It's been creating a lot of questions.
Yeah.
Good stuff.
All right. Well, let's take a break.
There's been a poll reversal at Brothers of the Servant podcast here. And
Beginning of the show.
we're doing the beginning of the show at the end. And it happened catastrophically and all at once. So yeah, end of show.
Yeah, we can.
Got some news stories.
relax.
Got some one-up boxes.
All my work is done.
You got to do Space Weather.
Take
News,
it away,
bud.
man. You fucking handle the whole rest of this. SpaceWeather.com. Where we get all our space weather news. The storm is not over. A geomagnetic storm that began on September 4th when a solar wind stream hit Earth is subsiding now, but it's not over. Minor G1 class storms are underway as September 4th turns into September 5th, and the solar wind is still blowing strong. High latitude skywatchers should remain alert for auroras. Current conditions, solar wind speed is 623.3 kilometers per second. The density is 8.95 protons per cubic centimeter. Sunspot count is 68. And the neutron count is 2.4% above the space age average. And the KP index is 5, which is rated as a storm. And the 24-hour max was 6. So there you go. There's your Space for the News for the week.
All right, now your job's over.
My jobs are, do we have, we got ag, we got rock and roll. What's the deal?
Yeah, well, I got
Press the
rock and roll.
wine. It's a 17-hour marathon of
That's
wine
right.
pressing took place last week.
Yes. And we got like 500 and, well, almost, let's see, what would that be? It's close to 600 gallons of Montepulciano.
Yeah, so we think 900 gallons total
Yeah.
ish.
And then 200
Of
and
red.
something of cab. And it already tastes better than any I've tasted out of the press that we've ever made.
Yeah.
It's really nice.
And we got to put them in one giant jug, which was cool.
Bought two new tanks.
Yeah.
So that was good. I'm kind of worried about them. You know,
Oh, we're going to handle it tomorrow.
new tanks sitting over there. Tomorrow's a holiday. I was thinking about taking the day off, but it's stressing me out.
We could take the day off.
I got to go pick up barrels, and we got to barrel it down. It's basically it's settling out now, and it's still fermenting. I mean, it's still bubbling a little bit, so there's still CO2 production taking place.
Yep.
Not completely dry. There's probably plenty of residual sugar, so it's just slowing down to the point that the effervescence doesn't push all the grape skins up to the top, which creates a blanket protecting it from oxidation. So once it slows down enough, the grapes start to sink, and then you've got a big liquid surface on the top. In an open top fermentation, then you've got the possibility of getting too much oxygen. So you got to press at that point, or put it in a closed container.
Right.
Which is called extended maceration. When you keep it in a closed container and you don't press and you just let it sit on those skins for longer.
Yeah.
We've done a little bit of that, but yeah, we pressed this off and
It's
took
really
a long
good.
time, and it tastes good.
Cab is great. Monty tastes good.
Yeah, I'm excited about it.
We also racked off the white.
And then we've got to start, so if we do go in tomorrow, we have to start secondary fermentation. Secondary fermentation is a bacterial fermentation where you use a malolactic bacteria, which converts the naturally present malic acid to lactic acid. It eats the malic acid and poops out lactic acid. That process can take months.
Yeah.
Hopefully it'll only take a month, but might need to warm it up a little bit in there to make it go a little faster.
Yeah.
So the difficulty now is if you're going to do malolactic fermentation, which we do on all of our reds,
Yeah, it smooths them out.
you don't want to put any SO2 in there. You don't want to stabilize the wine
Yeah.
because it would kill the bacteria. So
Yes.
this is the scary part because you have a possibility of the wine being spoiled by bacteria at this point, right? It's the yeast is not running the environment
Right.
anymore.
Yeah, during the main part of the fermentation, the yeast is completely in
Just
control
owning.
of the environment. Yeah.
And
Once it starts to
just
slow
some bad
down,
things
then-
can happen, but yeah, for the
Yeah.
most part, is pretty well protected. Yeah.
Yeah.
So now I've got malolactic bacteria in the freezer, so we gotta warm that up and add that to the to the wine, but you don't really want to add that when there's a bunch of lees in there.
Yeah, so we got to rack it off the lees.
It can create off odors and stuff. So we transfer the wine off of the lees, clean the tank out, put the wine back in the tank, then add the malolactic bacteria.
Yeah.
And hope that process starts getting going pretty soon. And so in a month or so, we'll be able to do our first SO2 additions, which will
start to stabilize it.
Yeah. Keep anything else from growing in it. So.
And then it'll sit in barrel for a year, you know.
Yeah.
8 months to a year.
Yeah. Or even longer.
Or longer, if we can afford it.
Yeah. We got some 2020 that's just, September, that's 24 months it's been in the barrels.
Yeah.
And it's
as a special
really
reserve.
Yeah.
So there you go. Oh, and the river's full. Maybe we said that in the last episode.
Maybe.
It just filled up one day.
Catastrophically.
Yeah.
Yeah.
So there you go. God dang.
Rock and roll update is no rock and roll.
People are having babies.
Lots of things are happening right now. Number one, we are in harvest season, so
Yep.
I've been working every weekend, except for this weekend, and finally I just literally sat on my ass and played video games with Soul up to this point.
Awesome.
I haven't done anything. I brought home one of the fermentation bins, filled it up with water, and we have a small pool.
Oh, cool.
Right in front of the porch. So
All
we've been
right.
getting in the pool, going back and playing video games. Come back outside, get in the pool, go back in and play video games. I've made a lot of... I beat Dragon Warrior.
All right.
The very first one on the actual Nintendo, the NES. Totally destroyed.
That's fantastic.
Totally destroyed.
What level did you have to
Dragon
get
Lord.
to?
I was all the way at level 24.
Wow.
And then I found out I just had a terrible strategy.
Oh, okay.
I ran away from all the bad guys until I got to him, and then I fought him, and I easily beat him.
Oh, yeah,
so
yeah.
I was like, dang, I should have done that when I was at a level 20.
Yeah.
Oh, wow.
I think that's when I beat it, was level 20 back in the
Yeah.
day. Yeah, you make a speed run at the very end.
Yeah. You just run away from everybody.
Yeah.
Anyways.
You're like, I'm busy. I got to go.
See, I never beat any video games up until recently. I just started okay, I'm going back to the first games, and I'm going to beat them. But it's just because Soul's, he's really into it. So I like to pull up these old games and be like, this
Sure.
is how we started, bro. And he calls it 2D.
2D.
He's like, let's play 2D Mario. It's like, all right. So I introduced him to Legend of Zelda. Obviously, that was the first one because I was playing. What's the one on the Switch? I just can't even think of the name.
Oh. Don't
Awesome
ask me.
game.
Yeah.
Anyway, Breath of the Wild, and
Yeah.
he's went all crazy about it. So then I was like, okay, well, let's play the very first
Yeah, let
one
me
'cause
show
it's
the
awesome.
origins here.
So we got 2D stuff, and then the normal stuff to him. Anyway, it's been a lot of fun. So
now
yeah,
you're gonna
going back to the this
Dragon
is-
Warrior 2?
Yeah, I was gonna look for it. Yeah.
yeah.
I need to get I don't have it, but I'll get it for the Switch. But this is part of the rock and roll update, right? I'm playing
Yeah.
video games and sitting on my ass. That's why nothing is happening. 2 band members their wives are about to have babies, so
Yeah.
it's any day now. So
Yeah.
there's not much going on there. And then the drummer has his company is opening or has been in the process of opening and building a badass store in Malibu in California. So he's
out of town.
So they're like, we need you out here. So he's going to be there for a month or 2.
Oh, okay.
So we're just kind of, it's like, okay, life gets in the way. So what we decided to do, because we were gearing up to let's go play some shows, let's record some live videos. And I'm just like, look, guys, this is obviously not happening. I was a little skeptical to begin with. I'm just like, let's just start working on the next album.
Yeah.
So I've got this list of songs. I've already started working on stuff. So we're going to just start in our, everybody in their location, doing it basically the way we did the other one. Hopefully much faster. Getting the rough drafts put together, getting all the parts done, and then we'll just book the studio and start, recording, doing the final recordings again.
Cool.
And then, when things work out, we will we'll play some shows, but I don't know. Who knows, man? I'm not even worried about it. I love creating. I love the creative process. So, but I haven't really posted anything of note on the Patreon in a while. I've been feeling really guilty about that.
Uh-oh.
So I need to do that. So there you go. That's my excellent. We also have 1-up boxes.
Oh yeah.
Should we do that now or at the end?
Yeah, let's do that at the end.
Okay.
What do you got?
I do want to read this NASA story related to. I looked it up based on the book here that you're going through, Path of the Pole, and I referred to it a couple of times. This is from NASA, 2012. Magnetic pole reversal happens all the geologic time. Scientists understand that Earth's magnetic field has flipped its polarity many times over the millennia. In other words, if you were alive about 800,000 years ago and facing what we call north with a magnetic compass in your hand, the needle would point to south. This is because a magnetic compass is calibrated based on the Earth's poles. The north-south markings of a compass would be 180 degrees wrong if the polarity of today's magnetic field were reversed. Many doomsday theorists have tried to take this natural geological occurrence and suggest it could lead to Earth's destruction. But would there be any dramatic effects? The answer from the geologic and fossil records we have from hundreds of past magnetic polarity reversals seems to be no. Reversals are the rule, not the exception. Earth has settled in the last 20 million years into a pattern of pole reversal about every 200,000 to 300,000 years. Although it has been more than twice that long since the last reversal. A reversal happens over hundreds or thousands of years and is not exactly a clean backflip. Magnetic fields morph and push and pull at one another, with multiple poles emerging at odd latitudes throughout the process. That's interesting. Scientists estimate reversals have happened at least hundreds of times over the past 3 billion years. And while reversals have happened more frequently in recent years when dinosaurs walked the Earth, a reversal was more likely to happen only about every 1 million years. Sediment cores taken from deep ocean floors can tell scientists about magnetic polarity shifts, providing a direct link between magnetic field activity and the fossil record. The Earth's magnetic field determines the magnetization of lava as it is laid down on the ocean floor on either side of the mid-Atlantic rift, where the North American and European continental plates are spreading apart. As lava solidifies, it creates a record of the orientation of past magnetic fields, much like a tape recorder records sound. The last time that Earth's poles flipped in a major reversal was about 780,000 years ago, in what scientists call the Brunhes-Matuyama reversal. Matuyama? Anyway. Those guys have strange names. The fossil record shows no drastic changes in plant or animal life. Deep ocean sediment cores from this period also indicate no changes in glacial activity based on the amount of oxygen isotopes in the cores. This is also proof that polarity reversal would not affect the rotation axis of Earth, as the planet's rotation axis tilt has a significant effect on climate and glaciation, and any change would be evident in the glacial record. Earth's polarity is not a constant. Unlike a classic bar magnet or the decorative magnets on your refrigerator, the matter governing Earth's magnetic field moves around. Geophysicists are pretty sure that the reason Earth has a magnetic field is because its solid iron core is surrounded by a fluid ocean of hot liquid metal. This process can also be modeled with supercomputers. Ours is, without hyperbole, a dynamic planet. The flow of liquid iron in Earth's core creates electric currents, which in turn create the magnetic field. So while parts of Earth's outer core are too deep for scientists to measure directly, we can infer movement in the core by observing changes in the magnetic field. The magnetic North Pole has been creeping northward by more than 600 miles since the early 19th century, when explorers first located it precisely. It is moving faster now, actually, as scientists estimate the pole is migrating northward about 40 miles per year, as opposed to about 10 miles per year in the early 20th century. Another doomsday hypothesis about a geomagnetic flip plays up fears about incoming solar activity. This suggestion mistakenly assumes that a pole reversal would momentarily leave Earth without the magnetic field that protects us from solar flares and coronal mass ejections from the sun. But while Earth's magnetic field can indeed weaken and strengthen over time, there is no indication that it has ever disappeared completely. A weaker field would certainly lead to a small increase in solar radiation on Earth, as well as a beautiful display of aurora at lower latitudes, but nothing deadly. Moreover, even with a weakened magnetic field, Earth's thick atmosphere also offers protection against the sun's incoming particles. The science shows that magnetic pole reversal is, in terms of geologic timescales, a common occurrence that happens gradually over millennia. While the conditions that cause polarity reversals are not entirely predictable, the North Pole's movement could subtly change direction. For instance, there is nothing in the millions of years of geologic record to suggest that any of the 2012 doomsday scenarios connected to a pole reversal should be taken seriously.
Oh, that's what it's
I
about.
forgot this story is in 2012. A reversal might, however, be good business for magnetic compass manufacturers. That's a good point. If I'm buying stock in compass manufacturers.
That's right.
If the Earth's magnetic pole shifts,
Bring in your compass. Yeah. We'll repaint the needle.
Oh my God, that's cool. Yeah. So
I have read that
I've always
there's no seemingly no evidence of
catastrophic destruction,
mass animal die-offs or anything like that associated with any of the magnetic reversal events.
Yeah, and I feel that too. I mean, obviously, if somehow something happened
but that's
that
just
sort
because
of caused
they all catch on fire. You're not going to find any fossils when they all burn to death.
The flipping of the pole, if it was still being sustained, in other words, seems okay. But if there is something that happens that sort of shuts it down somehow, which that seems hard to imagine.
Yeah.
It's just going to shut down. Okay. So I got another one here. This is from phys.org, and it's actually a reference to a paper in the Geological Society of America, which I sent to...
The Watcher says birds would fly north for the winter and die.
Hey, that's a good point.
Yeah. That is a really good point.
I wonder if there's any... Yeah.
They all fly south for the summer and die, or fly north for the winter and die.
That's a really good point,
It is
though.
a great point.
What about all these?
Yeah, don't all these migrating animals use the magnetic field for navigation? Isn't that the idea?
That would be interesting to look at in an evolutionarily.
Yeah.
Or if that's a word. But yeah, like if this is happening every 300 or 600,000 years or something, how do these animals
The migrating animals
evolve that capability over such long periods of time? They have to have a switch.
Yeah. That is interesting. Now I want to ask NASA about that.
That's really cool. That's a really good point.
That's a great
See,
point.
that's why we keep you around.
Yeah. Yep.
Profound profundities from the bag of chips. All right. This this paper is it's strange. The story is called "Crime Scene Technique Identifies Asteroid Sites," and I still haven't really figured out
What's the crime scene
how
technique?
this is a crime scene technique, but that's the way the publications have been about it. But of course, in the paper itself, I didn't see anything about that. But it's basically a way to find a new way to determine impact proxies, which I did send to George Howard and the Comet Research Group, because this would be great if they could use this method. Tens of tons of extraterrestrial solid material collide with Earth daily. Most of this material is small enough that it burns up in the atmosphere, but some fragments are large enough to cause quite a predicament. In 2013, a 20-diameter body exploded over Chelyabinsk, seriously injuring more than 1,500 people. The most recent impact crater on Earth was formed in 2007 when an asteroid crashed into a small village in Peru. A 1947 asteroid impact in far eastern Russia resulted in the formation of the youngest crater-strewn field on our planet. Sikhote Alin, I guess is the name of it. The most impressive, relatively recent extraterrestrial event happened in 1908 when a body exploded over Siberia, flattening 2,000 square kilometers of forest. We can prepare for this natural hazard only if we understand how often these kinds of small impacts happened in the past and how they influence the environment. A new article in the Geological Society of America, America's journal Geology, shows that analyzing bodies of organisms killed by an impact of asteroids can teach us exactly how much damage occurs at the spot of such a cosmic collision. The research team dug out trenches and rims of 4 craters. And they list the 4 craters: Kali, Maine, and Kali 2/8 in Estonia, Marasco in Poland, and Whitecourt in Alberta, Canada. So the 4 craters located on 2 different continents that formed thousands of years apart. Dr. Jury Plato and Dr. Argo Jolette noted that surprisingly, in all those places, we found the same thing: millimeter to centimeter sized pieces of charcoal intermixed within material ejected during its formation and located at the same place in respect to the crater. Dr. Ania Losiak, the lead author of this study from the Institute of Geological Sciences, Polish Academy of Sciences, and the University of Exeter, said, "At first we thought those charcoals were formed by wildfires that occurred shortly before the impact, and charcoals just got tangled in this extraterrestrial situation. But something was not right with this hypothesis. There were too many coincidences. Why would there be large wildfires shortly before formation of 4 different small impact craters divided by thousands of kilometers and years? Why would it be found only in a very specific location within the proximal ejecta blanket? It made no sense, so we decided to investigate further and analyze properties of the charcoal pieces found intermixed within material ejected from craters and compare it with wildfire charcoals."
Watcher says it's Exeter.
Exeter. Thank you, sir. Like bodies studied in a criminal investigation, the properties of organic remnants turned into charcoal reflect the conditions in which they were killed. Based on their properties, we can clearly recognize charcoals formed as a result of a wildfire and those found within proximal ejecta of impact craters. Okay, so that's the loose comparison here.
Okay.
Professor Claire Belcher from the University of Exeter explained, impact charcoals are really weird. They were all formed in much lower temperatures than wildfire charcoals. They lack sections that were formed while directly touching the flame, and they are all very similar to each other. While in a fire, it is common to find strongly charred wood just next to barely affected branches. This is definitely not what we expected when we started this study. We think that impact charcoals were formed when fragments of trees shattered by the impact were intermixed with local material ejected from the crater. This study improves our understanding of environmental effects of small impact crater formation so that in the future, when we discover an asteroid a few meters across or more coming our way only a couple weeks before the impact, we will be able to more precisely determine the size and type of evacuation zone necessary. Our research may also help to find new impact craters on Earth. This is to me the part that I'm really interested in. I mean, obviously we want to know how big of an evacuation area we would need, but still. No. What we really need to know is history. Our research may also help find new impact craters on Earth. We expect that we are missing, from our records, more than 10 craters formed within the last 10,000 years.
Wow.
We need to find them before their relatives visit us unexpectedly, explained Professor Wojtek Skuzinski from Adam Mickiewicz University in Poznan. Sorry. I do not know how to pronounce that last name. It's mostly consonants. Szczyucinski.
Wow.
Suzukinski. I'll just give it as Suzukinski. So then the other piece of this I have is I think this is pretty good here. This is from the paper. This is the abstract from the paper. The frequency of crater-producing asteroid impacts on Earth is not known. Of the predicted Holocene asteroid impact craters of less than 200-meter diameter, only 30% have been located. How do they know that? Until now, there has been no way to distinguish them from normal terrestrial structures unless pieces of iron meteorites were found nearby. We show that the reflective properties of charcoal found in the proximal ejecta of small impact craters are distinct from those produced by wildfires. Impact-produced charcoals and wildfire charcoals must derive from different heating regimes. We suggest that charcoal with specific reflective properties may help to recognize the meteoritic origin of small craters.
Wow.
So the thing that I think that's really important about that is that you don't even necessarily need an impact, right? You could probably find similar from a bolide,
An airburst
or whatever. So yeah, if the Comet Research Group can use this new way of identifying charcoal fragments as impact proxies, and then they go back to all these Clovis sites where they were pulling old data and looking at impact proxies there.
And they can compare the charcoal samples.
They can compare those charcoal samples and see if it has the
reflectivity that it,
And then bam!
Yeah. They can say, well, this fits
based on
the impact profile rather than the wildfire profile.
That's right. Because that's been one of the big arguments on the side of the skeptics is that, this is things created by wildfires and stuff. So how are carbon spherules different when they're created by wildfires versus impact proxies? Like there's an argument to be made there.
That's fantastic. So you sent that to George and
I sent it to George and Alan West. And then I got a email back from George where he had
sent it to the whole team.
He had forwarded it to the what looked like an organizational email for the team. And then there was one response from a team member who was like, "Oh, cool, we'll take a look at this."
Nice.
So I was like, yeah, thanks, George.
Fantastic.
So that's all I got for news stories today.
All right, well, let's do, if we got one-up boxes, we got donations, and then we'll wrap it up.
Yes, sir.
Let's see what we got here. Well, first I'll mention that we got, one of the one-up boxes we got was some prints of photos from the Snake Bros meetup from Josh.
That's
so thank you very much, buddy. Thank you. And I think one of those prints is supposed to go to old Marty, UFO Marty.
Buddy, we got you a print.
Yeah. Okay, these are books.
Is this from Ann? Which one is this?
Anne usually sends me.
Oh, yeah, it should be. No, there's no cereal boxes involved in there, so that can't be from Ann.
That's right. There's no macaroni and cheese boxes. No, this is from Chandra. This is from the books from the Conscious Life Expo. She says this is some light reading material. Making Contact, Preparing for the New Realities of Extraterrestrial Existence by Alan Steinfeld. The Divine Plan, Now and Beyond 2250 by Carolyn Corey. And, I have this book, Trinity by Jacques Vallée and Paula Harris. I've got this one. Thank you very much. I didn't have a physical copy though, so thank you, Chandra.
Next. There's a card.
A card. We're supposed to. A very fat cat. Says, happy birthday, Russ. This is from Ann.
Sorry, Ann. We're a month late on that.
No, I wasn't going to send you a cake, but I figured I should send a real card to make up for all those recycled envelopes. Yes, I need my space. It is
a hoodie.
A hoodie. It
It's a
says
nice-
I am wearing this. This is fantastic.
Man, I see the one time I say it's got to be cereal boxes. And there's none.
Well, surprise, this is not a book, not Egypt, not crochet, something for sky watching on your deck. May not need it for a few months. And maybe the cat will look after it for you until then. All the best to you and your family, always, from Ann.
And there's a second little piece in here.
Man, this hoodie is awesome. I need my space with stars.
Fidget blocks. The magnetic ones are nicer, but I thought magnets in the cube around all those electronics, maybe not. Yeah.
Oh, yes.
Small cubes that can turn into more than one cube.
Covered in space.
Thank you, Ann.
Thank you.
Fragile artwork. Okay. Up here.
Okay.
That.
This is from Greg. Greg?
Greg Mills.
Greg.
Yeah.
Hey, Snake Bros and Snake Sister Laura. I offered the enclosed painting to Russ in Tennessee. I hope you'll find a nice home for it in the 10 by 10 by 10 cube of science. When I met Russ in mid-March, I was on Sode 50. I have been all caught up for at least a month. I kind of regret getting all caught up because now I have to do the weekly wait for Sodes. Even though I listen to other casts, yours is my favorite, and I especially like the Discord. Speaking of which, I am finally on the Discord as Streamwalker. So for all the listeners who haven't joined the Discord, I encourage you to join and at least lurk. You will find the people who participate are intelligent, thought-provoking, often hilarious, always entertaining, and above all else, super friendly. So Russ, you have said many times that you don't like PDF files because of how inconvenient it is to read them on your Kindle. Have you thought of putting... Okay, he's giving me tech advice. Thank you. I hope all is well with all of you. I hope to see you on another trip somewhere not far in the future.
And here's the paintings. Look at these snakes.
Hey, check out the snakes.
Oh, it's one
Oh, yes.
together.
And he says that it was his daughter who did the painting.
Oh, wow.
Her name is Callie.
Oh, thank you, Callie.
Yes, those are beautiful. I hope I'm saying that right. Kaylee.
It's like this deep blue space snake.
That's
with
beautiful.
Glitter.
Yeah.
It's awesome. Thank you so much.
Thank you.
All right, and wait, is that it? That's it. Yeah, we again, it's been crazy busy around here,
Yep.
and we just have not. Laura has not checked the 1UP boxes for a long time, obviously, since there was a birthday present in there for August 1st.
Yes.
Thank you all so much. We really appreciate that.
Yes, thank you. And if you want to get a hold of us, brothersoftheserpent@gmail.com. By the way, I should say that the getting on the Discord is the way to get the address, the P.O. box, if you want to send stuff.
Don't send food.
Yes, please don't send food. I do have the... I don't want to put the address on the website for obvious reasons, even though it's a P.O. box. So the only way to get it really is to either email me and ask me, in which case you may or may not get a response, or you can get in the Discord and there's just a bot command, or you can ask anybody there and they can pull it up for you. That's the best way to get that. So, but email us, brothersoftheserpent@gmail.com, website, brothersoftheserpent.com. That's where all the podcast related stuff is, including links to join the Discord. Discord is great. It's an easy chat application to use. Our server is large in terms of channels, but it's fantastic. And once you get in there and sort of figure it out, it's not hard, and people are always willing to help. You can ask questions, and like Greg was saying, the conversations are fantastic. The people in there are really nice. You know, most of them. I'm one of the mean ones. There's other ones, just a couple. Kyle's also kind of mean in there. Kyle and I are not nice, but everybody else is pretty nice in the Discord. And Kyle and I are mostly not in there. So there you go. Most of the people are nice most of the time. So join the Discord. You can find that on the website. You can also find out how to support the podcast. We have the pyramid scheme, so you can support us through PayPal or Patreon. If you join the Patreon, you do get Patreon specific content. So there are episodes up there that are special for the Patreons, and then other cool little goodies that we add every once in a while. Some videos of Kyle hunting for artifacts, and we put the bumper music up there. A lot of people have said they've joined just to get the bumper music. So if you're interested in hearing the full versions of the bumper music without us talking over them and annoying you, you can join the Patreon and get that.
They're not all up there yet.
Not all of them. I'm slowly trickling them up there. You know? So,
well, thanks so much to everybody who supports the show.
Yes.
Really appreciate it. And yeah, it's just a pleasure.
Oh, and I should also mention that, so we got a donation from Ann last week that she was an executive
She wanted
producer
us
for the
to
show.
buy pizza for everybody.
Yeah, and she was saying that it's going to be hard for you to save it, to use it for your own purposes if you've already said on the show that it's for pizza for everybody at the Scablands. So she's like, you outed yourself.
Yeah, well,
Doesn't matter.
too bad.
Yeah.
If they want that pizza, I'd be like, sorry, bro.
Yeah. We don't care. Yeah, she gave it to us for pizza for you, but we're keeping it. Sorry. Needed a new microphone. All right, everybody. Thank you guys so much. We love you.
All the meals are budgeted already in the Scablands, so you know, if you come, you'll be fed. And so there you go.
That's right.
Thanks so much, Ann. I'll get him something. You know, I'll buy beers.
Yeah, that's going to happen anyway. Yeah.
All right, we love you. Always have.
Always will.
Good night, Adamu.
Get back to work.